Welcome to lecture 5.4. This is just going to be a small lecture focusing on the two types of strain that we're going to see in Newman projections for butane in the next lecture. Sometimes students have a bit of confusion when these two types of strain are brought up, as it's kind of challenging to disentangle them, but I'll do so here for you. So a strain is just a source of instability. Generally, something that's stable has as little strain as possible, and something that is more stable is getting more and more strained as you go. Now, when torsional strain is discussed, torsional strain is referring to something very specific. It's referring to eclipsing bonds in a Newman projection. Now, if we think about eclipsing bonds, and I'll draw a little example here, right? Bonds are composed of electrons. We know that each sigma bond has 2 electrons in it. So when we have staggered bonds like this, those electrons are pretty far apart from each other. However, in an eclipsed configuration, those electrons are a little closer. Now, that's not a massive deal, but electrons will repel each other, and that does introduce a type of strain. So it doesn't matter what these attached groups are. That isn't the point of torsional strain. Torsional strain is simply a yes-no. Are the bonds eclipsed? If so, there is torsional strain. Or if the bonds are staggered, there is not torsional strain. Steric strain is more commonly used in chemistry, and we'll see it going forward more often. Refers to stuff in space. And what I mean by this is if I have substituents on my ring, if I try to put 2 big things in the same place, they're going to bump into each other, and they're going to interact, and that's going to be another strain. So really, it's stuff in space bumping into each other. So I've prepared a couple small Newman projections here just to go through these examples. In case 1, this is one of the configurations of butane we're going to see in the next lecture. Here we can count the 4 carbons, so we have 2 methyl groups. This one in the front is connected to one of the carbons, so a 3rd carbon, and of course this back circle represents the 4th carbon for all 4 carbons. Now we can see that this molecule does not have torsional strain. So I'll say no torsion. And I can say that pretty quickly because we can see that these bonds are staggered. Since they're not overlapping, there's no torsional strain. However, we have these small hydrogens, and these aren't a huge problem, but then we have these methyl groups. Now, these methyl groups are drawn small typically, but remember that carbon-hydrogen bonds aren't very small. I mean, we drew one here and we drew it this long, so it's only fair to draw these ones that long as well. So let's redraw these methyl groups with 3, that's a chlorine, there we go, with 3 long bonds to hydrogen. And you can start seeing that we're going to have some problems here. As these methyl groups get close together, they start bumping into each other. And this can sometimes be referred to as a steric clash. Right? So this indicates to us that this molecule has steric strain. Now, in this course, we're not going to focus too much on how bad those steric strains are or quantifying it. Further on in organic chemistry, you might begin putting some numbers and doing some math here. But for now, just knowing the difference between torsional and steric strain is important. Now, let's look at our second example. Here, we have a bunch of small molecules, and maybe you could argue that since they're close together, there might be some level of steric strain, but generally, when I view hydrogens, I will say that there is no steric strain here. These are very small things. Right? 1 proton, 1 electron. However, we can see that these bonds are eclipsing. And that means that despite these hydrogens being small, these bond electrons are going to be repelling each other. And that means that this molecule does have torsional strain. So now that we know the difference between steric and torsional strain, let's move forward and do a Newman projection for a more complicated molecule that's going to have 4 different rotational isomers, butane.